Okay, this one is another question. We are going to use the principle of conservation of energy. So let us go through it and see what happens. A particle of mass 2 kilograms is attached to one end of the string of natural length 1 meter, and the other end is fixed to a point A. Initially, the particle is held at A and is then released to fall vertically downwards, and it then comes to rest at a point 1.5 meters below A. Find the modulus of elasticity of the string. So we feel free to do a simple sketch. This is our A. So this is fixed there. Then the other end, we are attaching a particle of mass 2 kilograms. So here we have 2 kilogram mass. Of course, it's going to be having weight acting on it. Get mass times D. Okay. Now, of course, they are telling us that our L is 1 meter. They are not telling us anything about the extension. It is okay. So now we say from here up to here, let us say it's 1 meter up to here. Of course, we are going to have a straight from here, which we are going to say let it be. If from here up to down here is 1.5 meters, they are not telling us the straight, but it's easy for us we can know. Because if from here up here is 1.5 and from here to here is 1, then this is going to be 0.5 meters. So we have our x, or you can see it's going to be 1.5 minus 1. So our x is going to be 0.5 meters. So now this is the point where we are going to have most of the things happen. So before the sprint starts, we want to know what is the velocity there, because the principle of energy, conservation of energy, from principle of conservation of energy. You know that our work done is given by the kinetic energy, then plus the potential energy. So you know that our done is given by lambda x squared over 2L, work done in an elastic string. Then it's going to be a half mv squared, then plus, this is going to be mv, now it's going to be x. Now, from here, we want to know, because from here we want to know the velocity from here up to here. So there we are going to say, from the third law of motion, u squared plus 2as. So we want to know what was the velocity from here up to here. Is that at A, our u is 0, and when you call this one A, then maybe let us call this one as the B. The velocity passes there. So our s, and then our s, and at and after 1 meter, our s of course is 1 meter. So putting there, I want that velocity is 0 squared is plus 2 g into 1, because it's falling. Now the acceleration is due to gravity. It's the force that is causing it to accelerate. So r v squared here is going to be 2g, which will be 2 times 9.8, which I can see my v squared here is going to be, this is going to be what? 19.6. So I want the v squared. Then from here, from lambda x squared, don't simplify because you want the v squared, you leave it there. 2L equaling to a half mv squared plus mg x. Now from here, We want a modulus of elasticity. So that here we don't have it, we don't have this, the only thing here. We have x, we have v squared, we have m, so everything is okay now. So our m is 2 kilograms. So now our lambda is 0.5 squared over 2 times 1 is a half times 2 times v squared, which is 19.6 plus 2 times 9.8, then times 0.5. This is the principle of conservation of energy for an elastic spring. Simple. Very easy. Okay, so from here I think we can see that this one is going to vanish. Then this is going to give us 1. So we have lambda 0.5 squared over 2 equaling 2. We add now 19.6 plus 9.8, which is 29.4. Applying that our lambda is going to be 29.4. Now I'll divide by 0.5 squared. So my lambda here is going to be times 2. It's going to be 235.2 newtons. And that would be the case with ease without any hassle. I think you see. The moment you see that they are giving you always this velocity, what we take note of is this velocity here. We determine that velocity before the stretch. So from here up to here, that's when the velocity is going. We want that velocity, the final velocity there, so that you can get the kinetic energy. Now, you can use the idea of loss in potential energy is equal to the gain in kinetic energy. You can also use that, no problem. But this one is a bit better. Or is this x, this h would have been the h. It's the distance now after the stretch. So this is the distance after the stretch that we are looking for there. So we expect that after it has reached its natural length, then we calculate for this distance. It is causing that distance for the stretch. That's where we put our x, and it's the x in the work done. This one is the v from here up to here. That's it, members. I wish you well.